in 1769, in England, English mine operators were using the power furnished by horses to pump water from flooded mines. Mine owners naturally thought in terms of the number of horses needed to do a certain amount of work. When James Watt invented a mechanical substitute for the power of horses in 1769, he wanted to know how much work it would do in comparison with a horse. So he and his assistant, William Murdoch, performed many experiments under various conditions, measuring the ability of different horses to raise heavy stone weights from a stone quarry pit. They found that the average horse, under average conditions, exerts the amount of power which would raise 550 pounds a distance of 1 foot in 1 second. Working continuously for 1 minute, the same power could move a total of 33,000 pounds a distance of 1 foot. Watt took this figure as a unit and called it 1 horsepower. The horsepower unit proved very useful. Watt was able to tell mine owners and businessmen exactly what size engine would be needed to replace the horses they'd been using. When the use of mechanical power became more general, Watt's horsepower unit was kept as a standard for estimating and comparing power. We can measure any energy in terms of horsepower. For example, it would take about 3 million ants to develop the power of a single horse. Sturdy legs and a strong back give the coolie more strength than the average human being. Yet, in action, he develops only 1/5 of a horsepower. While the elephant, having the advantage of his great size and huge muscles, can perform complicated tasks with the strength of 5 horses. As the needs of civilization have increased, gradually, machines have taken the place of muscles to develop power. Today, man gets power from many sources: the power of steam, the power of water and electricity, and the power of the internal combustion engine. As engines developed by man have grown more powerful, they have grown more compact. This perfect miniature engine has 4 cylinders, but it develops only 1 horsepower. On the other hand, the largest and most powerful internal combustion engines in the world, located at a power plant in Chicago, have only 4 cylinders apiece. But each of these giants drives a dynamo which generates enough electricity to do the work of 10,000 horses. It isn't the number of cylinders. It is the size and design that is important. In an automobile engine, likewise, there are many factors that control the amount and the kind of power. Feature by feature, part by part, cylinder by cylinder, the horsepower of automobile engines has been increased. Power and economy in the modern automobile engine result from the careful design of many features. The carburetor is designed to handle the gasoline efficiently and accurately to get the greatest advantage from the fuel. Intake manifold passages and valve openings are designed to supply quick reserves of power with economy. Precision-fitted pistons give stamina and durability. The cooling system keeps the engine operating at a constant temperature, developing full power at all times, and under all weather conditions. Every part has been designed with maximum strength for rugged, constant power, while friction-removing bearings and special lubrication permit sustained high speeds. The valve-in-head design has brought to the motor car the same flashing power that brings the thrill to riding in a speedboat, the same dependable power that is so vital in an air transport, combined with the maximum efficiency of the racing car, getting the last drop of energy out of a drop of gasoline. The modern motor car has these same features of design for extra power under all conditions of weather and road. Few people realize the great amount of power that travels with them under the hood of their automobile, theirs to control wisely and safely. Almost every and safely. Almost every family can have at its individual command the strength of 85 horses, eager and willing to respond, 85 horsepower, flowing smoothly at the touch of the accelerator.